Hello and welcome to our channel Stories in Biology. In this video I will discuss resolution of a microscope, the most important consideration for image formation apart from magnification. And I will also discuss what does it have to do with another parameter called the numerical aperture number of the objective lens. Let us first try to understand resolution and two allied terms associated with resolution, that is the limit of resolution and the resolving power. The English word resolve is the word from which the word resolution originated. In case of optical instruments, it means separately distinguish. Let's go deep into the phrase separately distinguish. Suppose these are 2 points on a specimen and they are having 1 millimeter distance between them. Yes, 1 millimeter distance mentioned here is not in exact scale, but with 1 millimeter distance interval between them, our eyes can easily distinguish them as separate points. Now, if we decrease the distance and keep them both at 0.1 millimeter away, our eyes can still be able to separately distinguish those 2 points. But what will happen if we continue to decrease the distance and make it less than 0.1 millimeter? Can we still be able to separately distinguish them as separate entities? No, we cannot. We will view them together as a big point, although we know that there still exists some distance between those 2 points, because the lowest limit of distance between 2 points that the human eye lens can separately distinguish is 0.1 millimeter. Like a human eye lens, every lens has got its own limit of distance, up to which it can separately distinguish 2 closely placed points. Or in other words, every lens has got its own power to distinguish points or objects located very close to each other. Keeping all this thing in mind, let us try to define resolution and the allied terms. Resolution is the smallest interval of distance between 2 points of a specimen that a lens can reveal them as separate entities, so that the image formed by the lens appears crisp and sharp. Okay, then what is limit of resolution? Limit of resolution refers to the same distance but the shortest distance, or the lowest range of distance between 2 points up to which a lens can distinguish 2 closely placed points and beyond which it cannot reveal them as separate entities. And now, resolution power or resolving power. By the term resolving power, we refer to the ability of a lens to distinguish closely placed points as separate points. To make it simple, we can say that lesser the limit of resolution between 2 points, higher is the resolving power of the lens. Or in other words, we can easily say that resolving power is inversely proportional to the limit of resolution. Hope these 3 terms are clear to you now. So, from the above discussion, we can say that resolution is the term by which we simply refer to a certain distance, and it is very much measurable and is represented by d. The equation we use to calculate it is d equals to 0.5 lambda upon n sin theta, where d is the minimum distance between 2 points of a specimen, or the limit of resolution, and lambda is the wavelength of light we use to illuminate the specimen, and by n sin theta we refer to the numerical aperture number of the objective lens. Now, before going into the details of the equation, let me remind you about the purpose of this video. It is to make a clear understanding of resolution and how resolution power is related to the numerical aperture number of the objective lens. And by doing so, we will also try to learn how resolution power of an objective lens can be increased. So far, we know that as d or limit of resolution becomes smaller, resolution power of the lens will increase. Looking at the equation in mathematical terms, we can say that to achieve higher resolution power, that is lesser limit of resolution, the numerator of the equation, or 0.5 lambda, should have to be lesser in value, and the denominator, or n sin theta, should have to be higher in value as much as possible. So apparently it is clear that if we have to achieve higher resolution power, we have to manipulate with the value of lambda and n sin theta. Or in other words, we have to find a lesser value of lambda and a higher value of n sin theta. So let's get acquainted with these parameters. The lambda, or the wavelength of light, and n sin theta, or the numerical aperture number of the objective lens. The wavelength spectrum of light used to illuminate the specimen is a major determining factor in achieving higher resolution power or lesser limit of resolution. The wavelength must be shorter than the distance between two objects or limit of resolution. In other words, the shorter the wavelength, the better the resolution. So we can say that we have to use light with shorter wavelength, particularly light at the blue end of the visible spectrum in the range of 450 to 530 nanometers. Now let's inculcate numerical aperture number, or n sin theta. We already know that we need higher value of numerical aperture to achieve higher resolution power, to produce highly dissolved image with higher clarity. Numerical aperture is a measure of the ability of the objective lens to gather light, and it is, as we know, is denoted by n sin theta, where n is the refractive index of the medium in which the lens works, and the theta is defined as half the angle of the cone of light entering the objective. Before going into the details of the numerical aperture, let me recapitulate some basics of light path followed in optical microscope. In conventional bright field optical microscope, the specimen on stage is lit from below by a cone-shaped beam of light. Actually, light coming from the source are condensed by the substage condenser to form this cone of light, which will hit the specimen from below. And after passing through the specimen, they will spread again to form an inverted cone of light and will enter the objective lens. This inverted cone of transmitted light will have its vertex at the specimen. A longitudinal slice of this inverted cone of light will show the angular aperture, and theta is the one half of the angular aperture. Just to remind you that the distance between the front of the lens and the surface of the cover slip or the specimen is defined as the working distance. And note that we were talking about the refractive index of the medium, or n, which is in this case is active in the working distance area. Okay, let's get back to our goal of achieving higher resolution power by increasing the numerical aperture number. We already know that the numerical aperture number is the ability to gather light by the objective lens. So to enhance the ability of gathering light by the objective lens, we have to bring a bigger cone of light into the lens. To attain this, we need to make a cone of light having a very wide angle. Or to be straight, we have to increase the value of theta. How can we do this? We can do this by simply reducing the working distance. This will result in the formation of a bigger cone of light with more diffraction orders, which then can be collected by the lens to form highly resolved image. But there must be a limit up to which the value of theta can be increased. The maximum value of theta can be 90 degree, and we know that the value of sin 90 degree is 1. So by reducing working distance, we had attained the maximum value of theta, that is 90 degree, and by doing so we got the maximum value of sin theta, that is 1. And if we put this maximum value of sin theta in the equation to derive numerical aperture, we are left only with n. It reveals that numerical aperture depends largely on the refractive index of the medium active in the working distance area. So to achieve higher resolution and a high numerical aperture value, we have to use a medium of high refractive index between the specimen and the objective lens. We know that refractive index of air is 1, and there are other high density mediums like water having a refractive index of 1.25, and there are some specialized oil emulsions having refractive index ranging from 1.25 to 1.51, like that of glass. So to achieve higher resolution power or resolving power, we need to replace air from the working distance area by one of these high density mediums like oil immersion, so that many light rays that did not enter the objective due to refraction at the surface of the objective lens and slide will now do so. Now, if we put the appropriate values of all the parameters in the equation, like 1.25 refractive index of a moderate oil immersion and 530 nanometers wavelength of a blue-green light, the maximum theoretical resolving power of a compound light microscope we can achieve is 212 nanometers or 0.2 micrometers. So before we conclude, let me recapitulate what we have learned today. The ability of a lens to distinguish closely placed points or resolving power depends on the parameters like wavelength of light, refractive index of the medium, and working distance of the objective. Higher numerical aperture permits increasingly oblique rays to enter the objective lens and thereon will allow smaller structures to be visualized with high clarity. Hope this makes sense to you. Please do subscribe to our channel Stories in Biology for more interesting stories from the world of biology. Thanks for being with me.